Hello friends, so once again welcome back to the class of physics, and now we are going to solve the question which will be based on your JEE Main pattern for again the chapter atoms. As you know, we have covered the theory of the chapter. Also we have solved many questions which were based on the NEET pattern and CBSE pattern, and what I can say, also I have given you so many examples in the chapter itself. So now it's time to just check whether we are able to solve the question for JEE Mains or not, right? So now we are going to start the question and we will see what will be our question number 1 before us. So if I just see, let me just tell you what we have discussed in the chapter. We have read about the Bohr's model, we have read about the energy levels, Bohr's quantization energy, so that we are going to cover over here and nothing else, right? So the question number 1 says that in hydrogen and hydrogen-like atoms, as my dear students, I have already discussed what are hydrogen-like atoms. Because hydrogen, as you know, hydrogen is what? 1H1, and if I am talking about hydrogen-like atoms, that means their atomic number is going to be differed by something. That will not be 1, their atomic number will be something else. So in hydrogen and hydrogen-like atoms, the ratio of difference of energies E4n minus E2n and E2n minus En, it varies with the atomic number Z and principal quantum number n. So we have to tell them what will be the ratio. Let me just tell you one thing. We have read one important formula of energy in this chapter, and this is nothing but, let me just tell you, this is E. If I will be writing in the form of En, that will be En equals to E1 upon n square, isn't it? Let me just tell you, we were writing E equals to minus 13.6 by n square, right? Now if I just want to find out the E for second shell, third shell, that will be E1 equals to 13.6 upon 1, right? E2 will be 13.6 upon 2 square, that will be 4. So can I write this E2 as E1 upon 2 square? So definitely it is going to be converted into this form if we are going to write it for n. So that means we are having En equals to E1 upon n square. So let me just start with the question now. We have been given E4n minus E2n. Now if I will be writing for E4n, that will be E1 upon 4n square, right students? And if I will be writing for E2n, that will be E2n equals to E1 upon 2n square. So my E4n will be E1 upon 16n square and E2n will be E1 upon 4n square, isn't it? Right? Now what I have to do? We have to take the difference of them, and also I have to take the difference of E2n minus En, and then we have to take the ratio of this. So what I am going to do is, just look at this side, I am going to write E4n minus E2n, and as I can see that E4n is E1 upon 16n square minus E2n E1 upon 4n square. As I have to take the ratio of E4n minus E2n and E2n minus En, so that will be E2n minus En. So if I am going to take the ratio of this, that will be, let me just, E2n will be E1 upon 2n whole square minus E1 upon n square. That will be the ratio. So that will be, if I will be just taking even as common, so I will be left with 1 upon 16 minus 1 upon 4 divided by 1 upon 4 minus 1 upon 1. That will be the answer, right? Now if you are going to solve it, you will see that your answer will come out to be 1 by 4. If you are going to solve this ratio, The answer will be 1 by 4. Now we have to check whether the option is available in the question or not. Okay, so if I am going to see here, I can see z square by n square, z4 by n4, z by n, and none of this, because I am having my constant value as 1 by 4. So I will be saying that my answer is none of these, right? So we have done the question number 1. And now let me just start with the next question of the session, that will be question number 2. Okay. So the question number 2 says, when an electron in the hydrogen atom in ground state absorbs a photon of energy 12.1 electron volt, its angular momentum will be what? Whether it will be decrease or whether it will be increasing. So let me just tell you once again, we will be taking a recap of what we have covered in the chapter, right? So if we know that if I will be showing you the energy levels, say this is n equals to 0, right? This is n equals to 1, this is n equals to 2, and this is n equals to 3. You know that if I will be talking about the energy levels, this E1 equals to 13.6, minus 13.6. This E2 is something like minus 3.4, I think something minus 3.4. And this E3 is nothing but minus 1.5 electron volt. This I am talking about approximate values. So if you are seeing in the question that electron in the hydrogen atom in the ground state absorbs a photon of energy 12.1 electron volt. So let me just mark a difference over here. If you are going to see this energy level and this energy level, the difference between them will be E3 minus E1, that will be minus 1.5 plus 13.6. So that means definitely it will came out to be 12.1 electron volt. That means your electron has reached up to the level of n equals to 3. Why we needed this n? What was the need of finding this n? Because to find out the angular momentum, what we need is, we need a electron shell, because we know that the formula of angular momentum is nh upon 2 pi. So to find out the nh upon 2 pi, we need the value of n, and so we have find it out right here. Okay, so now we know the value of n, and what we will do now, we will be finding out the angular momentum. Let me just start with writing the angular momentum. Earlier your angular momentum was, if I will be talking about the ground state, that will be nh upon 2 pi, or you can say n will be 1, so that will be h upon 2 pi. And in this case, the second case, L3, because the electron has been moved to the third shell. So your angular momentum will be 3h upon 2 pi. So to find out the difference, your delta L will be L3 minus L1, right? So what we have to do is 3h upon 2 pi minus h upon 2 pi. So you are left with h upon pi, right? So we know that the value of h is 6.6 into 10 raised to the power minus 34, and pi is nothing but the value 3.16. So we will be putting the value, let me just write it over here. Your value will be, your delta L is h upon pi. So 6.6 into 10 raised to the power minus 34 divided by 3.16. So if you are going to solve for this, you will see that your value will came out to be something as 1.12 into 10 raised to the power 11 or something. Or I am not going to write the definite value, because I am not going to do the calculative part over here. That is up to you, because I have to tell you the approach, so I am telling you. You need not to worry about the approach, because I am telling you here, you just have to worry about whether you are doing the correct calculation or not. So you are going to find out the value of this, and whatever will be your value of delta L, you will see that your value is coming out to be in positive or negative. So in that way you are going to see whether it is increasing or decreasing. So what we have did is, we have seen that our value has came out to be in positive. So that means our momentum is increasing. So let me just deduct what the options that will not be here. So definitely decreasing option are going to be cancelled out here. My options would be from either C or either D. So if you will be seeing that whatever value is coming out to be, that will be your answer. I don't know what will be the value, but I know that the positive value is going out to be arrived. So that means C or D, any one can be your answer, any of this option can be your answer depending on your calculation, isn't it? So you have to find out the answer. Now let me just move to the next question, that will be the question number 3 of this session. Okay. So in this question, what I can see that X-ray spectra has been arrived before me, and we have been given that in a characteristic X-ray spectra of some atom superimposed on continuous X-ray spectra. We have been given these two peaks P, Q, and we have been shown in the graph, this is lambda axis and this is relative intensity. What we have to tell is whether P represents K alpha line, Q represents K beta line, Q and P representing K alpha and K beta respectively, or the fourth option. So let me just repeat once again what are K alpha and K beta. Let me just tell you one thing. I have shown this thing in the theory also. See, these are energy levels. This is K, L, M, and this is N shell. Are you guys able to see this? Okay. So if this is N shell, I have told you what are K lines. The K lines are those lines which will be coming from any higher energy level to the K shell. So in this case, if the line is coming from N shell to K shell, that will be your K line. If it is coming from M shell to K shell, that will also be your K line, and L to K, that will also be your K line. Now if I am talking about alpha, beta, gamma, that will be the case of alpha, this will be K beta and this will be K gamma. That means if it is coming from L shell, that will be K alpha. If it is coming from M shell, that will be K beta, and if it is coming from N shell, subsequently it will be K gamma, and so on. Similarly, in this case, if I am going to draw for the L alpha and L beta line, so if it is coming from any higher energy level to the M shell, L shell, that will be your L alpha line. So here this will be your L alpha, this will be L beta. Now in this case, what I have to show you is, because here in this graph we have been given the lambda, and here the graph that I have been drawn before you is for energy. You can see that the energy of K alpha and K beta, what is the relation between them? You can see here K beta is having more energy than K alpha, because this is the energy axis. So you can see that K beta is having more energy than K alpha, right? Now you know the relation between frequency and wavelength. Energy is what? Energy is nothing but h nu. So that means nu of alpha is, right? Now the relation between nu and gamma is inversely proportional to each other. Since they are inversely proportional to each other, what I can write? I can say that the wavelength of K alpha, that would be greater than wavelength of K beta, right? So in this case, what I can see, wavelength of alpha is greater than beta. So here that will be wavelength, which wavelength is greater? Q wavelength is greater. So that means this should be K alpha and this should be K beta. So in this options what I can see, Q is representing K alpha and P is representing K beta. So Q alpha, and I think this one should be the correct answer, right? So now what we can see, we have done with the question and we should be now moving towards the next question, because we have cleared with this concept of K alpha lines, K beta, L alpha, L beta, that means the X-ray spectra basically. So we have covered it, and now we will be moving towards the next question of the session, and we will see what will be the next concept that is going to be arrived before us now. Okay. So what I can see here, as an electron makes a transition from an excited state to the ground state of a hydrogen like atom or ion, what is the condition that is going to be satisfied? We have to tell these, we have been given these energies, we have to tell whether kinetic energy, potential energy and total energy, what will be change in them basically, whether it is going to be decrease or increase. So before knowing this, we should know the formula for kinetic energy, for potential energy and for the total energy. So for that, we know that kinetic energy is nothing but, this is the formula of kinetic energy. And if I will be writing about potential energy, that is nothing but and you know that total energy is what? Total energy, you need not to remind this formula of total energy, you can find it out, kinetic energy plus potential energy. If you are going to add these two equations, then you will be having minus, this will be the relation for total energy. Now you are having three formulas before you. The formula for kinetic energy, potential energy and total energy. What is the important thing over here is that this energy, kinetic energy, this is inversely proportional to n square, and here your potential energy, this is inversely proportional to minus 1 upon n square. Similarly, your total energy, this is again inversely proportional to minus 1 by, directly proportional to minus 1 by n square. So in this case, if we are going to see that electron is making transition from excited state to the ground state. If it is coming from excited state to the ground state, that means your n is decreasing, right? So if n is decreasing, what should be happening? If n is decreasing, your kinetic energy should be increasing. Here, if your n is increasing, because here is, you can see one minus sign is there and similarly one minus sign is there. So if in this case your n will be decreasing, what is happening? Excited to ground, n is decreasing, so you should be also decreasing. Similarly here in this case, again your total energy will be decreasing. So now let me just move towards the option that are available before us. Kinetic energy decreases, potential energy increases, but total energy remains same. Wrong option. Kinetic energy, potential energy and total energy decrease. Again the wrong one. Kinetic energy and total energy decrease, but potential energy increase. Again the wrong one. Its kinetic energy increases, but potential energy and total energy decreases. So this option is the correct answer for this question, right? So what we have, what was important in the question is these formulas. if you forget these formulas, you would not be able to remind the relation between the N and the energy, right? So the important thing was the formulas. We will be now moving towards the next question of the session, and we will be watching what is the next question before us. Before that, I should clean the board for you. Okay. So the next question says that a hydrogen atom and a lithium ion are both in the second excited state. So my dear friends, what you need to understand over here is that if they are talking about the second excited state, that means, let me just say that this is my ground state. This is first excited state. This will be second excited state. So it will be coming from n equals to 0 to n equals to 1, n equals to 1 to n equals to 2. But basically if we start with the ground state, we consider here n equals to 1, right? So your first excited state will be n equals to 2 and your second excited state will be n equals to 3. This is your second excited state. So that means from this line we get to know what will be the value of n. Now if LH and LLI, that means angular momentum has been given, the momentum has been given for hydrogen and lithium are respectively electronic angular momenta and EH and ELI their respective energies. These both are the angular momenta and these both are the energy of them, and we have to tell them the relation between these two. Let me just tell you one thing. We know that we are having one formula of angular momentum. What is this formula? We have learnt in the chapter. Let me just write over here L equals to mvr, or you can write it as nh upon 2 pi, right? So in the very beginning they have cleared that your n will be 3 because they are saying that they are both in the second excited state, and from this information we have got to know that our n will be equals to 3. So let me just remove which is not required. We just need that our n has been came out to be 3. So if I will be talking about the hydrogen atom, so your angular momentum for hydrogen atom will be nh upon 2 pi because they both are in the same excited state. So that will be 3h upon 2 pi. Again for lithium that will be 3h upon 2 pi. So you can see here LH has been came out to be equals to Li. So that means one relation has been arrived. So let me just reduce the number of options. I can see that LH is greater than Li. Definitely this cannot be the answer. LH equals to Li. Yeah, I will be taking one conspiracy over here. Here also LH equals to Li again, but LH is less than Li. That cannot be possible. So now we have to check for the energies of them, right? We have covered the angular momenta part. Now we will be looking towards the energy. We know that if we will be talking about the energy of hydrogen like atoms, that will be equals to Z square by N square, or you can write over here 13.6 as well. This will be the formula for energy of any hydrogen like atoms, or you can write it as En equals to Z square E1 by N square, right? So for hydrogen, if I will be writing about the hydrogen case, Z is 1, so that will be 13.6 upon N square, right? Now if I will be talking about the lithium ion, we know that the atomic number of lithium is, here Z denotes the atomic number, and for the lithium atomic number is 3. So the square of 3 will be 9. So 9 into 13.6 divided by N square, or you can write it as well 9 into EH as well. So your energy for lithium has came out to be 9 times of EH. Definitely you can see that this energy of lithium has came out to be greater than the energy of hydrogen. So we can say that energy of lithium is greater than energy of hydrogen atom. So ELI is greater than EH. Now we will be moving towards the option ELI is greater than EH. So definitely this one will be the correct answer for this question, right? So now we will be moving towards the next question. Till then you can just take a note of this and then we will be beginning with that, okay? Okay. So now after doing this question, it's time to move towards the next question. That will be the question number 6 for this session, and we will be preparing the board. Okay. So I can see that we have been now the question of, we have been given the question for diatomic molecule. A diatomic molecule is made of two masses M1 and M2. Listen students, if we are, whenever we will be given the diatomic molecules and when we have been given these two values, that is M1 and M2, we can say that we can convert these two masses in one form, and that one form is called the reduced mass. So we can convert, and this reduced mass is denoted by mu. So let me just once write over here, this is reduced mass. So the value of your reduced mass then will be mu equals to M1 M2 upon M1 plus M2. You will be saying that, ma'am, you haven't started the question and you have started writing the formulas. But you know that my habit is that whenever I start reading the question, whatever values that is coming before to me, I just write it down. And from here I am getting the information that I can convert these two masses in one particular mass. So I am just writing it over here. And we have to calculate, okay, these masses are separated by a distance r. If we calculate its rotational energy by applying Bohr's rules of angular momentum quantization, its energy will be given by what? So basically we have to find out the energy. Now let me just tell you, we have been given that we have to apply this Bohr's rule of angular momentum quantization, and that rule is what? That rule says that L equals to mvr. Again your mvr will be equals to nh upon 2 pi. So let me just write over here, your L will be equals to mvr and that will be equals to nh upon 2 pi. Now because we have been using the terms angular momenta, angular kinetic energy, so from here we will be writing this m, because we have converted these two m's into one particular m. So I will be writing mu Vr equals to nh upon 2 pi. Now one more thing over here, you know that your angular velocity, it can be written as v equals to r omega. So in place of v you will be writing r omega and this as nh upon 2 pi. So that means you have came out to be mu r square omega equals to nh upon 2 pi. To find out the energy, what I can do is, let me just remove this and we will be finding out the value of energy. From here I can say that omega has came out to be nh upon 2 pi into mu r square. This is the value of omega. And now because I have to find out the value of energy, the rotational energy, You can see over here what we have to calculate, the rotational energy. So your rotational energy, the formula for that will be okay. As we know that the kinetic energy is half mv square. So from that you guys are gonna find by your own what will be the rotational kinetic energy. Let me just tell you the linear, if I'll be talking about in the linear form, this is the kinetic energy, and if I'll be talking about the rotational energy, I'll be putting in place of V, as I have told you over here, in place of V we are going to put r omega. So that means you will be having r omega square. So your rotational energy will be, let me just tell you that in place of this mass we once again write the reduced mass. So half mu r square omega square. This will be your rotational energy. Now let me just remove because this is not required now. Okay. So because we have find out the value of omega from here, this is the value of omega. What we can do is we can just put this value of omega into this equation, right? So I am going to put this value over here, that will be half mu r square into omega square. That will be n square h square, okay, n square h square by 4 pi square mu square r raised to the power 4. Okay. From here what I can see that this r square and this will be cancelled by 2 times, and anything else that will be reducing over here. Okay, this mu and mu is getting cancelled. So we are left with 1 by 8 n square h square divided by pi square into mu r square. This we have left with. Now what we can do is, as because in the options I can see that value has not been given in the form of mu, it has been given in the form of m1 and m2. So we are going to put the value of mu as this, right? Simple as that. So with what we are going to do is, I am going to rub this part, and now I am going to put this value in place of this. I will now be writing n square h square divided by 8 pi square into mu. Now your mu is m1 m2 upon m1 plus m2 into r square, right? So this we are left with now. Now we will be moving towards the options. In the options what I can see that in place of h we have been given this h prime, we have been given this, and you know that the value of this is what? The value of this is nothing but h upon 2 pi, and we are having the value in terms of h. So from here what I can do is h will be 2 pi into h prime. So your h will be what you are going to put? We are going to put this value into this equation, and then we will be finding the correct answer that has been written over here. So let me just come to this side. Okay. So we are now having the energy, rotational energy, let me just write it as RE, that means rotational energy, that is n square into h square. Now in place of h square what you have to do is, you are going to put h cross square into 4 pi square. 4 pi square into m1 plus m2. Till then you guys can do the calculation along with me. Here it is 8 pi square m1 m2 into r square. Now what you can do is, this pi square cancelled, this has been cancelled 2 times. Now you are left with rotational energy equals to n square h cross square into m1 plus m2 divided by 2m1 m2 r square. This is our final rotational energy, and we are now going to verify whether this is correct or not. So n square h square upon into m1 plus m2 divided by 2m1 m2 r square. That means this must be the correct option that is available in this options, right? Okay, what I can just see over here is that m1 plus m2 n square h cross square by 2m1 m2 m1 m2 r square. This option and this option are similarly, you will be saying that these are visibly same, but what is the difference? This is m1 square m2 square. So this cannot be the answer, this all will be neglected and this will be the correct answer. Okay. So now we will be moving towards the next question for the session, that will be the question number 7, and we will be applying what we have covered in the theory part. We will see whether we are able to solve the question or not. Okay. So in this question number 7, we have been given a energy level diagram, and few energy levels has been given, and we have to tell them that which transition shown represent the emission of a photon with the most energy. Let me just tell you what we have to do in this question is, this is a very simplest question, and what we can just neglect from here is that if we are talking about the emission of a photon, if we are talking about the emission of photon, that means you can directly ignore those options which are showing the energy levels in which electron is going from lower energy level to the higher energy level, because at that time your electron will be absorbing the energy. It will not be going to emit the photon, it is going to absorb the energy. So that means in this case from 1 to 3, from energy level 1 to 3, that means if I am going to talk about the first part, it is not going to show the emission of photon. Definitely this one option is going to be deducted from here. Now if I am going to talk about these energy levels, I will be checking which is the energy level which is showing more energy. Okay. So from here what I can just see that we have the value of energy as 1 upon nf square minus 1 upon ni square, where nf is your final energy level, ni is initial energy level. This is the formula for energy. What we are going to see in this case, it is coming from n equals to 4 to 3. We are talking about the second one. So your E2 will be RHC 1 upon, it is coming from 4 to 3. Okay. So whatever will be your value, if it is coming from 4 to 3, in this case 4 to 3, your value will be came out to be 0.05 RHC. If you are going to solve for this, you will see that E2, it has came out to be 0.05 RHC. Now we will be moving towards the second one. We have discussed about this and this. If I will be moving towards the third part, in this case electron is coming from 2 to 1. So in this case your 2 to 1, that means your final energy level is 1. 2 square is 4. So I am directly writing over here as this will be your energy for third one, right? Now if I will be talking about, we have discussed about this, if I will be talking about the electron that is coming from 4 to 2, that will be RHC from 4 to 2. Is that correct, whatever I am doing? You can check it out. If you will be taking the LCM of 4 and 16, that will be definitely 16, and 4 4s are 16, so 4, 16 1s are 6. So, okay. Now, if you are going to solve it, you will see that your value came out to be something like 0.2 RHC. Now, you will see that whether you are going to solve it or not, definitely I am knowing that you can solve it easily. So, I am directly writing it as 0.2 RHC. Now, what you can observe from here is that we have to tell them which is the most energy. So, here one thing that I have ignored was the first one, because in this case you will see that your energy will be coming out to be negative. So, that option will be directly deducted. Now, in these options 0.05, 0.75 and 0.2, this is the maximum energy that is coming out. That means, if it is taking transition from 2 to 1, that will give us the maximum energy, and this is about the third one. So, that means this will be the correct answer for this question. The third one is coming from 2 to 1. Okay? So, this was the simple question that we can just say that it was a theory part. If you would have covered this theory and formulas importantly, or with your pure mind, you can say, then that will be easy for you. Okay. So, the next question says that we have been given one thing, that is hydrogen atom. It is excited from ground state to another state with principal quantum number equals to 4. So, that means n has been given equals to 4. Then the number of spectral lines in the emission spectra will be what? Let me just tell you, my dear friends, these all are the questions that has been picked up from the number of previous year question and the number of sample papers. So, you cannot ignore, you cannot afford to ignore such questions which are the simplest one, because you know what happens, the person, the student who is preparing for JEE Main will be watching the typical question first, and in the exam you will be, when you will be seeing the simplest question, you will be just putting your so many efforts in the solving the question, whether the question will be of you can say the simplest question, the just formula based question. So, no need to put efforts in that question. For example, this question is just a formula based question. If we are somewhere seeing that we have to find out the number of spectral lines, the one formula that we know is Nn minus 1 upon 2. This is equals to number of spectral lines. So, that means what we are going to do now is we are going to put the value of n, because we have been given this value. So, here your n is 4. So, put this value 4 into 4 minus 1 divide by 2, 12 by 2, that means 6. So, your number of spectral line is 6. If you know this formula, you can easily solve the question. And let me just tell you, this is one previous year question, right? So, you cannot afford to ignore such question. The simplest answer is 6 over here. Okay? Now, let me just move towards the next question of the session, that will be your question number 9. Okay. In a hydrogen-like atom, electron makes transition from an energy level with quantum number n to another with quantum number n minus 1. If n is very much greater than 1, the frequency of radiation emitted is proportional to what? So directly what I can see here, we have to apply the formula of frequency, because we have to tell the relation between frequency and the quantum number, right. So we know that the formula for frequency is RC(Z) square 1 upon NF square, that means final energy level, minus 1 upon Ni square. Okay. So this we have before us. What I can do is, we know that electron is making transition from energy level with quantum number n to n minus 1. That means your final quantum number, final energy level will be n minus 1, initial will be n. So we are going to put over here, you will be having RC(Z) square 1 upon final, that means n minus 1 square minus 1 upon n square. So we can solve for this. Just open it, we will be having n square minus n minus 1 whole square divided by n square into n minus 1 whole square. So if you are going to solve for this, you will be having a square plus b square minus 2ab divided by n square into n minus 1 whole square. So from here what you can see, n square cancelled, you are left with 2n minus 1 divided by n square into n minus 1 whole square. So I will be writing it as nu equals to, that means frequency equals to RC(Z) square into 2n minus 1 divided by n square into n minus 1 whole square. Now just focus on the question what has been given over here. If n is very much greater than 1, we have to just apply this situation over here now. Let me just tell, if n is very much greater than 1, so what we can do? We can ignore this value. So we will be writing it as nu equals to RC(Z) square 2n. We are going to ignore this value 1. So we are left with 2n divided by, okay, let me just first of all write, if we are going to apply this situation, this 2n minus 1 will be converted to 2n and this n minus 1 whole square will be converted to n square. So we will be now writing it as RC(Z) square into 2n divided by n square into n minus 1 square, that means n square. So if you will be writing it as, you will be finding out that, let me just write it, RC(Z) square, this 2 will be taken out and this n will be cancelled out, you will be having 2 upon n cube. So that means your nu has came out to be proportional to 1 upon n cube. Definitely you can see from here. So we will be saying that the frequency of radiation emitted is proportional to 1 upon n cube. So A option should be the correct answer for this. Right or wrong? We have just approached from the correct way and we have reached to the situation where we can see that it has came out to be proportional to 1 by n cube. So this is the correct answer. Now we will be moving towards the next question without wasting much of our time. Okay, and this question is going to be the last question of the session. Okay, we have been given that a diatomic molecule has moment of inertia I. Okay, first of all let me just remove this previous question so that you are going to note the question that I am going to write here for you. Okay. So that we have been given the moment of inertia. by Bohr's quantization condition. Again Bohr's quantization condition. Let me just tell you friends that in this chapter the question that will be coming from in your JEE Main and JEE Advanced, that will be basically from the same topic, that is Bohr's model, X-ray spectra and like this. So again the same question, Bohr's quantization condition we have to apply. By Bohr's quantization condition, its rotational energy in the nth level where n equals to 0 is not allowed, that will be what? Again the simplest question. What we have covered this question earlier also, this question has been modified in one another form, and you can see that this is also a previous year question if you will be watching the previous year question. So you can see that the question has been modified in another form, but the level is same, the language is same, everything is same, but option has been differed, right. So we will be start with, because we have to use the Bohr's quantization condition, and that says that MVR equals to NH upon 2 pi. You can write it as, because I know that I can write this MVR as mR square omega, isn't it? So I will be writing it as mR square omega equals to NH upon 2 pi. Now because we have been given the moment of inertia, we know that I equals to mR square, right. So your I equals to mR square, what we are going to use it, we will be using it here. So your L will be equals to I omega, right. Now I omega equals to NH upon 2 pi. So from here what I can do is I can find out the value of omega, that will be NH upon 2 pi into I. Now because I have to find out the rotational energy, I know that formula for rotational energy is nothing but, let me just write it as rotational kinetic energy. This will be half I omega square. Again if you will be writing starting with the half mv square, and you are going to put the angular velocity in that, you will be having this same formula. So from here I am going to put the value of omega into this. Omega is nothing but NH upon 2 pi I. So we are going to put it here. The value will be n square h square divided by 4 pi square into I square. So you will be having this I and I will be cancelled once, n square h square divided by 8 pi square I. This will be the rotational kinetic energy. Now we have to focus over the whether this option is available or not. N square h square divided by 8 pi square I. N square h square divided by 8 pi square I, that must be the correct answer for this question. So we have covered the 10 question in this session, because we just have to check the level of the question for JEE Main. We have completed this exercise, and now we will be meeting again in the session where we are going to solve the question for JEE Advanced. Till then you guys get prepared for the question, just keep revising the formulas, just keep revising the concept. We will be meeting again. Just take care. Bye bye.